Okay, just a few minor loose ends to tie up with the IMF topic. The term van der Waals forces, apologies for the American accent. Van der Waals forces is a term, it's sort of an umbrella term now. The IB used to use it interchangeably with London forces, but now it's a broader term. And they use it to cover London dispersion forces. Now, right, this diagram just says dispersion, but that's what we've been calling London forces or London dispersion forces, and then dipole-dipole forces. It also technically covers something called a dipole-induced dipole force, where a polar molecule can induce a dipole in a nonpolar molecule. It's not really an important force for the IB. So for you, you just need to remember van der Waals forces. That term is a term that includes both dipole-dipole forces and London forces. However, it does not include hydrogen bonding. That doesn't get included under the umbrella term of van der Waals forces. I have seen it come up on paper one questions. Seems like a rather minor point to me, but they could ask you about it. Okay, so be aware of the term van der Waals forces. We mentioned previously with water solubility this idea of an ion-dipole interaction. So this is the interaction between an ion, something with a full charge, and something that's polar, like water, and it can explain water solubility of ionic compounds. Another topic that we don't tend to go into much, and neither does the IB, but you should be aware of it, is nonpolar solubility. We mostly focus on things that are soluble in water, but many things are not soluble in water. We know oil isn't soluble in water. A lot of organic compounds are not very polar. They're mostly nonpolar, and they aren't very soluble in water. So nonpolar solubility is actually super important for organic chemistry. And so things that are mostly nonpolar, like oils, but also things like iodine, is a simple two-atom molecule, completely nonpolar because it's symmetric. Iodine is much more soluble in nonpolar solvents than it is in water. So nonpolar solvents could be things like hexane. There are other ones like toluene and turpentine and all these other things, but mostly what they have in common is they tend to be mostly made out of carbon and hydrogen. There are others that have sort of an in-between solubility, things like acetone or propanone, which is a little bit polar, things like dichloromethane, CH2Cl2. These are slightly polar, and so they're sort of in between. They're good at dissolving things that are also slightly polar, as opposed to being really, really nonpolar, like hexane, or being highly polar, like water or water-soluble compounds, things with hydrogen bonding capability, or things that are ions. So solubility, really there's a whole continuum of solubility. So water solubility is one simple category where you're looking for hydrogen bonding with water molecules. Nonpolar solubility is sort of on the other end of the spectrum, looking for things that are largely hydrocarbon based that will mix well with other things that are fully nonpolar. And then you've got sort of these solvents, these various shades of gray in the middle, things that have slightly different polarities. And when doing things like extractions, like extracting caffeine out of tea or something like that, you really need to pick the right solvent that can dissolve the caffeine out of the tea or out of the liquid tea that you've made. So when the caffeine is in the water, you can then pull the caffeine from the water into a different solvent where the caffeine dissolves better. An example of that is this dichloromethane, DCM as they call it. It's a really good solvent for caffeine. It can pull the caffeine from the water into an organic, more nonpolar layer. And a final note, if I skim past all of this, is don't forget about the giant covalent structures. So although this was something covered previously in the unit, giant covalent structures like graphite and diamond, they do like to bring these up in comparison to molecules. And the key idea is that all we've been talking about with molecules and IMFs are very, very different than these giant covalent structures. So remember that IMFs are much, much weaker than covalent bonds. So you've got your London forces, you've got your dipole-dipole forces, and you've got your hydrogen bonding, and that's the order of their strength. And then you've got covalent bonding, much, much stronger than that. So even though we talk about hydrogen bonding as the strongest force, these structures like diamond, where there's only covalent bonding going on, or like silicon and silicon dioxide, those substances are going to have such higher boiling points and such higher hardness and things like that, because they only have really strong covalent bonds, as opposed to in between molecules we have these relatively weak intermolecular forces.